And now this is kind of the twist of a variable coefficient heat equation problem. Okay. We take, let's say 15 minutes with that. And you can chime in with questions if you have them.
Is it related to like considering a ball and all that, like all those derivations that we proved in class?
So that was for elliptic equations, right? So yeah, I guess that's why it's good to review this. Yeah, so remember for elliptic equations, we proved a mean value principle first. And then we basically, yeah, we strung all these balls together to prove the maximum principle. The weak maximum principle for heat is just using conditions on what a maximum would be on the interior of the domain, and proving it by contradiction that the maximum has to be on the boundary. So the first part would probably just be to make sure you remember what the weak maximum principle is. And obviously, if you get stuck, you can look it up for yourself. All right. Well, hopefully you had a chance to at least get started on it. Does anybody want to talk about this problem?
Can we do the same thing that you did in class, like consider v, which is like an additional quadratic term on u, and then find the condition on like v. I mean, by having it satisfy the partial differential equation, and then find a condition on epsilon, and then yeah, like find it in different regions, like find v in different regions.
Yeah, that's
Like,
the idea. Yeah. I mean, the point is the logic of, the constant diffusion coefficient case survives, because you still have you can write what's called like sort of a subsolution for the case where you add, where you perturb the solution. So so I guess, the way, as I was saying, the way you want to kind of set up the solution, right? So basically the problem is what? It's prove the weak max principle for continuous solutions. And actually I guess continuous solutions here, right? They're not too specific, right? So you might say, well, I'm worried about whether they're C2 or not. I think we would need these to be C2 in this case in order to write out our conditions on the second derivatives. So probably that should have said at least C2. But yeah, the logic essentially follows from what we did in class. There should be an open interval here. And for the heat equation, right, we set the n time to be some finite time, right? And A is continuous, right? And it's actually bounded from below by a value that's above 0, by a positive value. But I think actually, I don't know if it actually makes a difference whether or not it ever reaches 0 or not. Okay. So what's the max principle, first of all? Okay. Well, you have to kind of define your domains carefully, right? So if we let u sub t be the intersection of x is from 0 to 1, open interval, and t is from 0 to t, where this is open and then this is closed, right? So you have to do something special on this end boundary, okay? And then we call this thing gamma t, which is the closure with ut removed, okay, is its parabolic boundary. So yeah, if u is essentially c on u sub t, and it's c2. Sorry, this is the closure of u sub t. If it's c2 on just u sub t, and satisfies our IBBP there, okay, then the following thing is true, right? So max over the closure is equal to the max over just the parabolic boundary, okay? And I'll use this point to ask a couple questions. So first of all, what's the minimum principle? What's the weak minimum principle?
Same thing, but with the minimum.
Right. Okay. How would you, if we knew that the maximum principle was satisfied, how would we prove the minimum principle?
You consider negative u and then maximize that.
So if you need to prove the max and the minimum principle, you only need to do the hard work once. And then, yeah, you just flip the sign of u and you apply the minimum principle. Okay. All right. Another question. Is there this is a weak maximum principle. Is there a strong maximum principle for the heat equation? Yes or no?
Yes.
Okay, what is it?
If the domain is connected, then every point on the interior is strictly less than the maximum on the closure, or I guess the maximum on the boundary, or the function is constant and equal to the maximum, I guess.
Yes, yeah, that's good. Yeah, so it's this sort of either or, right? So either you have a non-constant function and it's strictly bounded from above by the values on the boundary, or it's just a constant function, right? Okay, good. All right. So let's
Question.
Yeah, go ahead.
I realized often when we're saying that something has to be C2, I'm not sure if we actually mean it has to be C2 or twice differentiable.
I mean, it's, yeah, continuously differentiable on the domain.
Right. So, but C2 means that the second derivative is continuous. Right?
Yeah, so it's twice, yeah, sorry, twice continuously differentiable.
Okay, why can't it just be twice differentiable? Maybe I'm missing something here.
Because you need the second derivative to be I see. So you're saying, could you have a situation where the derivative is piecewise defined?
Yeah, like the second
Derivative
would
is
be-
piecewise defined,
Yeah.
for instance. And would that break anything in this case?
I don't necessarily see where it would break something.
Yeah.
I guess just for the sake of notation, it's easier to write C2 than write out twice differentiable.
That it's twice differentiable, right? So that, yeah, there. Yeah, so maybe it's one of those sufficient, but not, you could probably back off and have it still be a necessary condition. But yeah.
Okay,
maybe
I was just wondering.
Maybe it's mild overkill. Yeah, I'll have to think about that. So as we go through, yeah, let's see if we run into any places where we really need continuity of the second derivative. So the second derivative comes up for sure. I don't know if there's some bizarre construction you could have for a particular function that whose second derivative is defined, but it's not